Good morning, students. I am Dr. K. Chandrasekar, Professor in Department of Aeronautical Engineering, PSM College of Engineering and Technology, Tirunelveli. Today I am going to give a lecture on composite materials and structures. First we see the definition of composite material. A composite material which is composed of two or more materials at a microscopic scale and have chemically distinct phases. Composite material heterogeneous at a microscopic scale but statistically homogeneous at macroscopic scale. In composite material, constituent materials have significantly different properties. Composite materials are made by combining two or more natural or artificial elements, that is, with different physical or chemical properties that are stronger as a team than as individual players. Composites are typically designed with a particular use in mind, such as added strength, efficiency, and durability. Generally, a composite material is composed of reinforcement, that is fibers, particles, flakes, and or fillers. They are embedded in a matrix like polymers, metals, or ceramics. The matrix holds the reinforcement to form the desired shape, while the reinforcement improves the overall mechanical properties of the matrix. When designed properly, the new combined material exhibits better strength than would each individual materials. Examples of composite system include concrete reinforced with steel and epoxy reinforced with graphite fibers, etc. Then we see the classification of certain materials as a composites. Combination of materials should result in significant property changes. The content of the constituents in composite material is generally more than 10%. So each constituent should have constitute more than 10% of overall weightage. In general, property of one constituent is much greater than 5% than other materials. Then we see the history of the composite material. One of the earliest use of composite material was by the ancient Mesopotamians around 3400 BC, when they glued wood strips at different angles to create plywood. The concept of composite building construction has existed since ancient times. Civilization throughout the world have used basic elements of their surrounding environment in the fabrication of dwellings, including mud or straw and wood or clay. Bricks were and still are made from mud and straw. In the 12th century, Mongol warriors used composite materials like bamboo, silk, cattle tendons, and horns and pine resin to craft archery bows that were swifter and more powerful than those of their rivals. They put the tendons on the outer side and sheets of horn on the combustion, that is inner side of the bow, over the core of bamboo. They tightly wrapped the structure with silk and sealed it with pine resin. A museum tested some of the surviving bows, now more than 900 years old, and found that the old bows were nearly as strong as modern ones, and it would hit targets as far away as 490 yards. That is it's equal to the length of nearly 5 football fields. In the late of 1800, cannon builders began experimenting with different materials to make proper laminates. They tried gluing layers of craft paper together with shellac. It was a good idea, but ultimately flopped because the available material were not up to the task. The first synthetic, that is man-made resins that could be converted from liquid to solid, the process called polymerization, were developed between 1870 and 1890. These polymer resins are transformed from the liquid state to the solid state by cross-linking the molecules. The 1930s heralded a new era for resins and ultimately the composites industry as a whole. Unsaturated polyester resins were patented in 1936 by Carleton Ellis because of their curing, that is hardening properties. They become the primary choice for resins in composite manufacturing. By the late 1930s, other high-performance resin systems had become available, including epoxy resins. This chart shows evolution of the materials from 10,000 BC to 2010. How the polymers, composites, ceramics are the importance of the materials given in the year. Some of the example from today to day-to-day life. Straw bricks, one of the composite material. Concrete, RCC concrete. Wood, there is combination of cellulose and lignin. Human body with combination of muscles and bones. Tires, plywoods, sports goods, etc. Then the evolution of the materials, particularly the composite material. The use of modern composite materials evolved during World War II for military application and non-metallic shielding of radomes to host electronic radar equipments. They mainly used glass fiber reinforced plastics, GFRP. The first application of wood composite laminates is used in Havilland mosquito fighter bomber of British Royal Air Force. During World War II, the attack on Pearl Harbor by Japanese they used torpedo bomber. The most of the parts made up of composite material in that bomber. Then advantage, you see the advantage of composite material. Composite materials have high resistance to fatigue and corrosion degradation. They have high strength or stiffness to weight ratio. As enumerated above, weight savings are significantly ranging from 25 to 45% of the weight of conventional metallic designs. Due to greater reliability, there are fewer inspection and structural repairs. Directional tailoring capabilities of the composite material to meet the design requirement. This is one of the advantages of composite material. The fiber pattern can be laid in a manner that will tailor the structure to efficiently sustain the applied loads. Then fiber to fiber redundant load path. Improved tent resistance is normally achieved with the composite materials. Composite panels do not sustain damage as easily as thin gauge sheet metals. It is easier to achieve smooth aerodynamic profile for drag reduction. Complex double curvature parts with a smooth surface finish can be made in one manufacturing operation. So composites offer improved torsional stiffness. This implies high drilling speed, reduced number of intermediate bearings and supporting structural elements. The overall part count and manufacturing and assembly cost are thus reduced in composite materials. Composite materials have high resistance to impact damage. Thermoplastics have rapid process cycles, making them attractive for high volume commercial application that traditionally have been the domain of sheet metals. Moreover, thermoplastic can also be reformed. Like metals, the composite materials, the thermoplastics have indefinite shelf life. Composites are dimensionally stable. That is, they have low thermal conductivity and low coefficient of thermal expansion. Composite material can be tailored to comply with the broad range of thermal expansion design requirements and to minimize thermal stresses. Manufacture and assembly are simplified because of part integration, thereby reducing cost. The improved weatherability of composites in a marine environment as well as their corrosion resistance and durability reduce the downtime for maintenance. Close tolerance can be achieved without machining. The material is reduced because composite parts and structures are frequently built to shape rather than machined to the required configuration as in common with metals. Excellent heat sink properties of composites, especially carbon-carbon composite, combined with their lightweight, have extended their use of aircraft brakes. They have improved friction and bearing properties. The ability to tailor the basic material properties of a laminate has allowed new approaches to design of aeroelastic flight structures. Then some of the limitation of composite material. Composite materials have high cost of raw materials and fabrication. Composites are more brittle than rock metals and thus are more easily damaged. Transverse properties may be weak. Matrix is weak, therefore low toughness. The reuse and disposal of composite material may be difficult and it is difficult to attach. Repair of composite material introduces new problems for the following reasons. Materials require refrigerated transport and storage and have limited shelf life. Hot curing is necessary in many cases requiring special tooling. Hot or cold curing takes time. Analysis is difficult. Matrix is subject to environmental degradation also. Then some areas of application of composite materials. Almost all the areas in the today's life we are using composite materials. Aerospace and military, civil, electronics, energy, automobile and transportation sectors, sports sector, medical instruments and medical area, and marine and so on. So some of the applications in aerospace of the composite material. So use of composites in LCA Tejas. In this LCA Tejas, glass composites, Kelvar composite and carbon composite are used. The figure shows how the composites are used in LCA light combat aircraft Tejas. Then light combat helicopter, the various parts are made up of carbon glass composite, Kelvar and carbon composites. So the figure shows the parts of the LCH. This is a helicopter blade. So in this carbon fiber, glass fiber, the composites are used in this helicopter blade. And CFRP, carbon fiber reinforced polymers, reinforces valve first single engine light sports aircraft. An Italian startup company is manufacturing Bell's first single engine light sport aircraft composed almost entirely of carbon fiber reinforced polymer. Two-seat high performance aircraft is designed for pilot owners who want to travel in comfort and safety. NASA and Boeing build and test all composite cryogenic tank. Cryogenic rocket fuel tanks to contain liquid hydrogen or liquid oxygen fuels at cryogenic temperature that is below minus 238 degree Fahrenheit. The high energy propellant in the tank is required for extended human exploration missions beyond low Earth orbit. NASA and Boeing have now successfully built and tested all composite CFRP 5.5 meter diameter tank. It's a part of the composite cryogenic technology demonstration project. One of the largest and lightest cryogenic liquid hydrogen fuel tanks ever manufactured. It is planned 8.4 meter tank that would reduce the weight of rocket tanks by 30% and cut launch cost by at least 25%. The use of the composite, the use of out of autoclave manufacturing process, they produce 8.4 meter tank. Of course, so the BMW i3 is a trendsetter. It's made up of CF. Most parts are made up of CFRP composites. The CFRP internal structure is used in internal structure and body. The year introduced 2011. The production volume is 70 vehicles per day. The manufacturing process to manufacture the composite parts is RTM, that is resin transfer molding. The Volkswagen diesel powered plug-in hybrid car, approximately 21% of car is made from CFRP. The production began at 2013. The volume is 250. Manufacturing process is RTM. This is a concept pickup track. In this track, CFRP bumpers, tailgate and inner cargo box are used. This close molding process is used to manufacture the composite material parts. The figure shows wind turbines. The vacuum assisted resin transfer molding is used to manufacturing the GFRP turbines. This 53-foot catamaran. In that CFRP hull used vacuum infusion processing method is used to produce the hull. Military surveillance ship, fiber reinforced polymer hulls, decks, pilot cores and structural arms are used by using composite materials. They introduced in the year of 2014 3 vessels for the government of Mozambique is manufactured using vacuum infusion processing. This military surveillance ship was produced. The desalination plant, in that GFRP pipes are used. Nearly 1.3 miles of piping they used in this plant. Filament binding process used to produce this GFRP pipes. This Australian company makes foldable boat with fiberglass. This is a folding boat, flat back, quick assembly 12-foot boat. Cantilever method they are used to produce the parts of the boat. So, in automobile industry, motorcycle racing helmet used to produced by CFRP helmet, shell reinforced with carbon fiber fabric, bladder molding process used to produce. A hydroplane race boat, 2-piece CFRP hulls used in this race boat, vacuum infusion processing used to produce. This is a green concept vehicle with composite panels. CFRP truck panels are used in this truck. Heat accelerated vacuum assisted infusion method used to produce these panels. Then we move to classification of composites. Broadly, the composites are classified into particle reinforced composites, fiber reinforced composites and structural composites. So further, the particle fiber reinforced composites are classified into large particle and dispersion strengthened. Then fiber reinforced composites are further classified into continuous, that is aligned, discontinuous. Further, the discontinuous can be classified into aligned and randomly oriented. Then structural can be classified into laminates and sandwich panels. We will see one by one. First, fiber reinforced composite materials. Okay. The fiber based on the filament with a length by diameter is very high. A composite with fiber reinforced is called fibrous composites. Fibers are the most important class of reinforcement. Fibers very strong. They provide significant strength and improvement to the material. Example, fiberglass. It is a continuous glass filaments in a polymer matrix used in this fiberglass. Strength, it has high strength due to fibers. Polymer simply holds them in place. The performance of a fiber composite is judged by its length, shape, orientation, and composition of the fibers and mechanical properties of the material. The alignment of fiber. First one is the you can align the fibers into transverse direction or longitudinal direction. The first figure shows aligned continuous. Then next classification is discontinuous. In discontinuous, aligned is second figure shows the discontinuous aligned fibers. Then the third one is randomly aligned discontinuous fibers. Then structural composites. Yeah, structural composite is normally composed of both homogeneous and composite materials. They are called layered composites. That is layer, lamina, ply. Any of the term used to call this type of layered composites. The materials comprising of layers of materials bonded together is called layers, laminates. Maybe several layers of two or more materials occurring alternatively or in a determined order more than once and in as many numbers as are required for specific purpose. Usual fiber orients are 0, 90 degree, plus or minus 45 degree. By combining this orientation, the desired strength and stiffness is achieved. Plane isotropy can be achieved. Fiber layers arranged in a way so that the strength is maximized and weight is minimized. Laminated composites must always be symmetric with respect to their middle plane, and they must also be balanced to avoid irregular distortion in the structure. This figure shows from the middle plane, above the middle plane, first layer is 90 degree and 0 degree, 0 degree, 0 degree. Like that, the top to bottom they are aligned symmetrically. A piling of woven materials without any bonding does not have any structural use, therefore a matrix needed. Exclusively unidirectional composites are never used. The figure shows unidirectional layered composites, quasi-isotropic layered composites. Then sandwich panels, two external strong layers that is called face sheets attached to a layer of less dense material that is core with low stiffness and low strength. Role of the face sheet is they withstand most of the plane loads and transversal bending stresses. The face sheet material alloys, fiber reinforced plastics, titanium, steel and plywood. Core material separates both face sheets and resists deformation perpendicular to the face plane. Provide resistance to shear stress along the planes perpendicular to the face sheets. The figure shows the sandwich panel. In sandwich panel, core materials may have different structures, polymer foams, synthetic rubber, inorganic cement, and balsa wood. Typical core with honeycomb structure is thin layers arranged in hexagonal cells. The figure shows a sandwich panel with honeycomb core. The application of these sandwich panels are ceilings, floors, and walls in the buildings in the aerospace industry, particularly in wing coating fuselage. The figure shows the sandwich panels. Then furtherly we can classify the composites by using reinforcement, that is discontinuous, stronger, harder. In matrix, continuous, discontinuous. Okay. The function of reinforcement is contribute desired properties and load carrying capacity, transfer the strength to matrix. The function of matrix is it holds the fibers together, protect the fibers from environment, protects the fiber from abrasion, helps to maintain the distribution of fibers, distributes the loads evenly between fibers, enhance some of properties of the resulting material and structures component. These properties are such as transverse strength of lamina, impact resistance. They provide better finish to final product also. Okay, based on the type of matrix material used, you can classify the composite as polymer composites, metal matrix composite, ceramic composites, carbon and graphite composites. The types of matrix materials are thermoplastic. Thermoplastics are softened upon heating and can be reshaped with heat and pressure. Thermoplastics have one or more two-dimensional molecular structure, and they tend to at an elevated temperature and show exaggerated melting point. Another advantage is that the process of softening at elevated temperature can reverse to regain its properties during cooling. Examples of thermoplastics are polypropylene, PVC, polyvinyl chloride, nylon, polyurethane, polyether ether ketone, that is called PEK, polyphenylene sulfide, PPS, polysulfone. The thermoplastics have highest toughness, high volume, become low cost processing, temperature ranges greater than 225 degrees centigrade. And thermoplastics are increasingly used over thermosets because of the following reasons. Processing is faster than thermoset composites since no curing reaction is required. Thermoplastics composites require only heating, shaping and cooling. The better properties of thermoplastics are high toughness and damage tolerance, low moisture absorption, chemical resistance, and they have low toxicity, but the cost is high. Then thermosetting becomes cross-linked during fabrication and do not soften upon reheating. They have qualities such as well-bonded three-dimensional molecular structure after curing. They decompose instead of melting on hardening. The examples for thermosets are polyesters, epoxies, polymerides, other resins. The polyesters have low cost, good mechanical strength, low density and versatility, good electrical properties, good heat resistance, and cold and hot molding can be used. The curing temperature is 120 degree centigrade. Thermosets. In thermosets, the next one is epoxy. Epoxy resins are widely used for most advanced composites. The advantage of epoxy resins are low shrinkage during curing, high strength and flexibility, adjustable and curing range, better adhesion between fiber and matrix, better electrical properties, and they have resistance to chemical and solvents. Some of the disadvantages of epoxy resins are somewhat toxic in nature. They are limited to temperature application range up to 175 degrees centigrade. Moisture absorption is affecting the dimensional properties of the epoxy resins. High thermal coefficient of expansion, then slow curing. Then polymers. They have excellent mechanical strength. The excellent strength retention for long time in the range of 260 degree to 315 degrees centigrade range, and short term in 370 degrees centigrade range. Excellent electrical properties. The polymers have good fiber resistance and low smoke emission. Hot molding under pressure can be used to manufacture. Curing temperature is 170 degrees centigrade and 315 degrees centigrade. Problems with using polymer matrix materials are limited temperature range. They have only limited temperature range. The susceptibility to environmental degradation due to moisture, radiation, atomic ion in space. Low transverse strength. They have high residual strength due to large mismatch in coefficient of thermal expansion, both fiber and matrix. Polymer matrix cannot be used near or above the glass transition temperature. Then go for metals, metals like aluminum, titanium, copper, higher use temperature range. Aluminum matrix composite can be used in the temperature range above 300 degrees centigrade and titanium at 800 degrees centigrade. They have high transfer strength, toughness. The absence of moisture and high thermal conductivity they are having. The disadvantage of metal matrix composites are they are heavier when compared to polymers. They're more susceptible to interface degradation at fiber matrix interface and to corrosion. Then ceramics composites. Carbon, the materials can be used carbon, silicon carbide and silicon nitride. Ceramic have used very high temperature range is greater than 2000 degrees centigrade. They have high elastic modulus and they have low density. The disadvantage of ceramics matrix composites are brittleness, easily they break, susceptible to flows. Then carbon matrix composites. Carbon fibers in carbon matrix are used in the carbon-carbon composites. They are used under extreme mechanical and thermal loads for space applications. The advantages of carbon matrix composites are low specific weight, high heat absorption capacity. They have resistance to thermal shock, high resistance to damage. They have exceptional frictional properties at high energy levels. The resistance to high temperatures, the chemical inertness is high, low coefficient of thermal expansion. The disadvantages of carbon matrix composite materials are low resistance to oxidation above 500 degrees centigrade. They have high cost of materials and manufacturing. Okay. Based on the form of reinforcement, you can classify the composites into fiber, viscous, flake and particulate. The advanced fibers are fibers possessing high specific stiffness and specific strength. They are glass, carbon, organic, ceramic. The natural fibers are, the example for natural fibers are, in animal fibers, we can use silk, wool, spider, sinew, camel hair and etc. In vegetable fibers, cotton, jute, bamboo, sisal, mass, cam, abaca, coir, kabak and etc. So many vegetable fibers are used in composite materials as a fibers. In mineral fibers, asbestos, basalts, mineral wool and glass wool, they are used as fiber. Okay. Glass fibers, the ancient Egyptians made containers from coarse fibers drawn from heat softened glass. They produce by extruding molten glass at 1200 degrees centigrade and they passed through spinnerets of 1 to 2 mm diameter, then drawing the filament to produce fibers of diameter between 1 to 5 micrometer. Individual filament is small in diameter, isentropic in the behavior and very flexible. Okay. The variety of forms of glass fibers are E class, S2 class, R class, C class, D class. E class, they have high strength and high resistivity. S2 class, they have high strength, modulus and stability under extreme temperature, corrosive environment. R class are enhanced mechanical properties. C class they can resist corrosion in an acid environment. In D class, they have dielectric properties. In general, glass fibers are isotropic in nature. Then carbon fibers. Carbon-carbon covalent bond is the strongest in nature. Thomas Edison made carbon fiber from bamboo when experimenting for light lamp. The difference between carbon and graphite fibers are carbon fiber contains 80 to 90% of carbon and graphite fiber contains more than 99% carbon. The carbon fiber is produced at 1300 degrees centigrade while carbon fiber is produced in excess of 1900 degrees centigrade. In general term, carbon fiber used for both fibers, made from two types of precursor materials, PAN, that is polyacrylamide nitrate, rayon patch. Then carbon fibers, precursor fiber is carbonized rather than melting. Filaments are made by controlled pyrolysis, it's a chemical deposition by heat of a precursor material in by fiber form by heat treatment at temperature 1000 to 3000 degrees centigrade. The different fibers have different morphology, origin, size and shape. The morphology is very dependent on the manufacturing process. The size of individual filament ranges from 3 to 4 micrometer, hence very flexible. Maximum temperature of use of fibers ranges from 250 degrees centigrade to 2000 degrees centigrade. Properties changes with the temperature at high temperature. The maximum temperature of use of composite is controlled by the use of temperature of matrix. Modulus and strength is controlled by process thermal decomposition of the organic precursor under well controlled conditions of temperature and stress. Heterogeneous microstructure are consisting of numerous laminar ribbons. Thus, carbon fibers are anisotropic in nature. Then organic fibers, aramides, that is aromatic polymeride. It's called aramide fibers. It's a family of nylons. Melt spun from a liquid solution. Morphology is radically arranged crystalline sheets resulting into anisotropic process properties. Filament diameter about 12 micrometer and partially flexible, high tensile strength, intermediate modulus. They have very low elongation up to breaking point, significantly lower strength in comparison. DuPont developed these fibers under the trade name Kelvar from polyphenylene terephthalate polymer. 5 grades of Kelvar with varying engineering properties are available: Kelvar 29, Kelvar 49, Kelvar 100, Kelvar 119, Kelvar 129. They have different engineering properties. Then ceramic fibers. Boron. It was the first advanced fiber developed for structural application. A ceramic monofilament fiber manufactured by CVD on to a tungsten core of 12 micrometer diameter. Fiber itself has a composite circular cross section. It has circular cross section. Fiber diameter ranges from 33 to 400 micrometer and typically diameter of 140 micrometer. Boron is brittle, hence large diameter results in lower flexibility. Boron have thermal coefficient mismatch between boron and tungsten, resulting in thermal residual stress during fabrication cool down to a room temperature. When coated with SiC or boron carbide, silicon carbide or boron carbide can be used to reinforce light alloys. Strong in both tension and compression, exhibit linear axial stress strain relationship up to 650 degrees centigrade. The high cost of production. Ceramic fibers are aluminum Al2O3. These are ceramics fabricated by spinning a slurry mix of alumina particles and additive to form a yarn, which is then subjected to controlled heating. Fibers retain strength at high temperature. Then silicon carbide, ceramic fiber. The method used to manufacture in silicon SiC is CVD on tungsten and carbon. Carbon pyroleric graphite coated carbon core SES6. This fiber is similar in size and microstructure to boron. Relativity stiffness size is of 140 micrometer. The second method is Nicolan by Japan, controlled by pyrolysis of pyromeric precursor. Filament is similar to carbon fiber in size. up to approximately 14 micrometer is more flexible. Silicon carbide shows high structural stability and strength retention even at temperature above 1000 degrees centigrade. The cross-sectional shape of fibers may be circular, elliptical, triangular. Okay. In circular shape, glass, carbon, organic fibers, aluminium, silicon carbide fibers are used. In elliptical shape, alumina molite are used. In triangle shape, silicon carbide whiskers are used. Okay. Then hexagonal sapphire whiskers are used. Rounded triangular sapphire single crystal fiber used. Kidney bean carbon used. Trilobal carbon triangle are in this shape. Then fiber and matrix system. The notation of fiber matrix system is fiber bar matrix. That is, example is carbon epoxy. So in this carbon epoxy, carbon is fiber, epoxy is matrix. Class epoxy. In this class is fiber, epoxy is as a matrix. In Kelvar epoxy, Kelvar is used as a fiber, epoxy is used as a matrix. The proportion of contents must be mentioned as a volume fraction. Okay. For example, AS4 bar big. So AS4 is in this carbon composite material. AS4 is fiber, big is matrix. T300 bar 5 to the 5208. T700 bar M21, IM8 bar epoxy. Then nickel bar epoxy, boron, aluminium, ACS6 bar titanium 153, S2 glass bar epoxy. In this S2 glass is fiber, epoxy is matrix. Okay. This table shows the properties of fiber and matrix materials. Okay, metals, fiber and matrix materials. Okay. Then whisker reinforced composites. A whisker has essentially the same near crystal sized diameter as the fiber, but generally is very short and stuffy, although the length to diameter ratio can be in hundreds. Whiskers have preferred shape and bud are small both in diameter and length as compared to fibers. Single crystals grown with nearly zero defects are termed whiskers. They are usually discontinuous and short fibers of different cross section made from several materials like graphite, silicon carbide, copper, iron, etc. The typical lengths of whiskers are in 3 to 55 nanometer ranges. Whiskers differ from particles in that whiskers have different length to width ratio greater than 1. Whisker can have extraordinary strength up to 7000 megapascal. Okay. Then flakes. Flake composite consists of flat reinforcements of matrix. Typical flake materials are glass, mica, aluminium, and silver. Flake composites provide advantages such as high out of plane structural modulus, high strength, and low cost. Flakes are often used in place of fibers as can be densely packed. Metal flakes that are in close contact with each other in polymer matrix can conduct electricity or heat, while mica flakes and glass can resist both. Flakes are not expensive to produce and usually cost less than fibers. Okay. The figure shows the flake reinforced composite. While angle playing is difficult in continuous fibers, which need to approach isotropic properties, it is not so in flakes. Flake composites have higher theoretical modulus of velocity than fiber reinforced composites. They are relatively cheaper to produce and be handled in small quantities. Then particulate. Particulate composite consists of particles immersed in matrix such as alloys and ceramics. They are used isotropic because the particles are added randomly. Microstructures and metal and ceramics composites which show particles of one phase strewn in another are known as particle reinforced composites. Various geometrical shapes they can have cubes, spheres, flakes, etc. And the particles are made up of rubbers, metals, and plastics. Generally, they have low strength. Okay. The figure shows particulate reinforced composite. Despite the size in particulate composites is of order of a few microns and volume concentration is greater than 28%. Particle composite have advantages such as improved strength, increased operating temperature, oxidation resistance. Typical example include use of aluminum particles in rubber, silicon carbide particles in aluminum, and gravel, sand, and cement to make the concrete. So today we discuss about the introduction of composites and classification of composites. Thank you.